Hello everyone, welcome to our channel Code with Sunny, and in this video we will be talking about the problem sum of total strength of wizards. Its index is 2281 and it is the hard problem in the LeetCode. Okay, so before moving on, let me talk about the prerequisites that is being required to solve this problem efficiently. Like we need to know the concepts of dynamic programming, as well as we need to know the concepts of how we are going to use a monotonic stack to find out next greater element and next smaller element similarly. Okay, and also we are going to do some pre-calculations, prefix sums and suffix sum, so you must have to be aware about how we are going to do that efficiently. So let's begin. We are given a zero indexed integer array strength, where strength of I denotes the strength of the ith wizard. So basically we will be given an array of size n, and every element of the array is going to denote the strength of the particular wizard. Now for a contiguous group of wizards, that is for a subarray, the total strength of integers, like total strength of this subarray, is defined as the product of the following two values: the weakest wizard in this group and the sum of all the individual strength of the wizards. So in other words, if you need to find out the strength of a subarray, you need to product the minimum element, as well as you need to find out the product of minimum element and the sum of this particular subarray. And our task is to compute the sum of all the total strength of all contiguous group of wizards. That is, we need to find out the sum of all the total strength of every subarray. Since this answer can be very large, we need to return it modulo this prime number, 10 raised to the power 9 plus 7. I will talk about the examples. First, let's look over the constraints. So you can see the max length of the array is 10 raised to the power 5. So it gives us the idea that O of n square time solution will not be accepted. So we will be focusing on O of n time and O of n space solution. So here in this video I will be dealing with O of n time and O of n space efficient solution. So let's begin to understand this problem with the help of examples. So here you can see I have taken one example from the example 1, and the size of this array is going to be 4. So there will be total 10 subarrays. You can see I have extracted every subarray and written down the strength of these subarrays. Now for every subarray, the strength is going to be written as the minimum element. Here you can see minimum element is 1 and the sum of the subarray is 1. So here 1 is the strength of this subarray. Similarly, if you look out at this one, the minimum element is 1 and the sum of the subarray is 4, so the strength of the subarray is 4. Now if you sum up all those values that we have obtained for every subarray, you will get the 44 as our answer, and this is matching with the required desired output. Now to compute, to find out the every subarray and find out their strength, the summing up all those values, it is quite a hectic task, because you can see you are having the max length of the array 10 raised to the power 5. If you do that, you will get O of n square time, extracting every subarray and finding out their strength. So that will give you a TLE verdict. So you need to find an efficient way to build up the solution to find out the answers efficiently. So let's focus upon that, how we are going to do that. Okay, so what I will be explaining first is the concept of next greater and next smaller element in short. Okay, suppose we have this array and we have to find out the next smaller element of this A4 to the left as well as to the right of this index. So it is basically we are going to maintain a stack, monotonic increasing stack, maintain a stack. Okay, that will help us in finding out the next smaller element to the right of the current element as well as to the left of the current element efficiently. Okay, so what I will do is I will keep the elements in the stack. Let's take an example and understand how it is going to be done. Suppose it is the array is 1 3 1 2. Okay, so I will maintain a stack. I will maintain a stack of the elements like this. Suppose we have element 1 in the stack, so I will push it into the stack. Then again 3 will come. Okay, so I will push up 3 into the stack again, and when 1 will come, 1 is the element which is smaller than 3, right, and it's present to the right of this 3. So it means that the first smaller element to the right of the element 3 is 1. So I will assign the element 3's position. The next smaller element of this element 3 is the position of the element 1. Okay, so this is the next smaller element. Okay, so also while finding out these things, like while stack top is strictly greater than this value 1, I will pop out the element. Okay, so 3 will be popped out, so stack top will become the element 1, and again 1 will come, so it will be pushed into the stack. Again 2 will come, it will be pushed into the stack. Now you can see we are left with this stack only. Okay, so only 3's next smaller element to the right of this 3 is present, which is at this position. Okay, now you can see once smaller element to the right of this 1 is not present, because every element to the right of this 1 is strictly greater than 1. Similarly, for 3 you are going to get the next smaller element over this position, and for this one you are not having any next smaller element. For this 2 you are not going to have next smaller element. Okay, now this is for every index we are able to find out the next smaller element to the right of this current index. Okay, now what if we iterate from the back side? If we iterate from the back side, we will get next smaller element to the left of this current element. Okay, so let me take an example and explain you how things will work. Okay, so 1 3 1 2. Okay, now we will iterate from the back side, so we will have encounter 2. Okay, now when we encounter 1, it will be pushed into the stack, but we are maintaining an monotonic increasing stack. Okay, so when we have this one, I will compare this with the stack top. Now you can see 1 is smaller than the stack top. It means that 2's next smaller element is over this position. So I will assign the next smaller element whose next smaller element of this 2 as the position of this element. Okay, so I will pop out this element and I will insert 1 into the stack. Okay, now note that 2's next smaller element is over here. Now again 3 will come. Now 3 is strictly greater than 1, so I will push 3 into the stack. So stack will contain 1 and 3. Now again 1 will come. Now when 1 will come, you can see 1 is strictly less than 3, so 3 will be popped out from the stack, and we will assign 3's next smaller element as 1. Okay, so this will be done like this, and 1 will be inserted back into the stack. So stack will contain 1 and 1. Now why we are able to do that? Because every time we are maintaining an monotonic increasing stack. Now this is the concept of next smaller element for every index to the left of it and to the right of it. Okay, if you are getting the problem, I will recommend to do this one, next greater element and next smaller element. You are going to find the same similar approach it is. Okay, so this is the main concept. Okay, now let's talk about how we are going to. Okay, so for every subarray we need to find out the minimum of the subarray in the range L to R multiplied by the sum of the subarray in the range L to R, right? Okay, now you can see for every subarray this minimum element changes, so it gives us the idea that why not we fix this minimum element and try to compute out the length of the subarrays that is being required, that is the subarray that covers this minimum element. Okay, we need to compute all those subarrays and find out the sum of the required subarrays, and we will multiply that subarrays that we have found with this minimum element, and that will be our answer corresponding to this current minimum element. Okay, if you are not getting this, no need to worry about. Let's take an example and understand how it will work. Okay, suppose I am going to fix this A4 as the minimum element. Okay, so we need to find all those subarrays which have A4 as the minimum element. Okay, we need to find all those subarrays which has A4 as the minimum element. Okay, now you can see first I will take this subarray A4, and then I will take A3 to A4, then I will take A2 to A4, then I will take A1 to A4. Okay, so these are all those subarrays. Like there are more subarrays, I will all include all those. For now let's understand, like A4 is the subarray that includes A4. Similarly from A3 to O4, A2 to A4, A1 to A4. Okay, and note that why I'm stopping over here. Suppose I'm assuming that at this position there lies an element, let's say AI, which is strictly less than A4, and similarly here lies an element AJ which is strictly less than A4. Okay, so it means that how we are how we are being able to find out this AI and AJ. It is very much simple. You can see for this position I am claiming that this A4 is the minimum element, and I am including the subarrays to the left, which is A1 to A3, and to the right A5 to A6, and after that we are not going to include like the subarrays that would lie over here and the subarrays that would lie over here. It means that all these elements A5, A6 as well as A1, A2, A3 is greater than or equal to A4. Okay, it means that next smaller element to the right of this A4 is this AG, and similarly next smaller element to the left of this A4 is AI. Okay, if we are able to find out this AI and AJ, then we can easily claim that A5 to A6 is the region of the subarray to the left, to the right of this A4, where we can extend our subarray. Similarly A1 to A3. Okay, so that's why we are computing the next smaller element for every index to the left as well as to the right of it. Suppose A1 to A3 is the feasible subarray and A5 to A6 is the feasible subarray for left positions and right positions respectively. Okay, so as I have said, we are going to take A4, similarly A3 to A4, similarly A2, A3 and A4, similarly A1, A2, A3 and A4. Okay, these all subarrays include A4. Now you can easily understand there are more subarrays that is going to include A4. What about the right positions of subarray end at this position? We are going to say we have the subarray from A4 to A5, we have the subarrays from A3 to A5, we have the subarrays from A2 to A5, we have the subarrays from A1 to A5. Similarly, the right end of the subarray will lie over A6, so we can have subarrays from A4 to A6, A3 to A6, A2 to A6, A1 to A6. Okay, so these are all the required subarrays. Okay, so like how we are going to find out the required sum efficiently. Let's try to focus over that. Okay, so as I've already said, we are going to fix this minimum element. Now what I will do is like I will divide this entire segment A1 to A6 into two parts. Okay, and we will try to find out the subarrays that will always include this minimum element. Okay, so we will divide this subarray from A1 to A6 into two parts, that is A1 to A4 including the minimum element, and A5 to A6. Okay, now what is the reason behind to do this partition? It basically it helps in finding out the sum efficiently. If you are able to compute this sum, the sum of all those subarrays where the minimum element lies, if you are able to find out the sum, we will multiply that sum with the value A4, and yes, we have done with this minimum element A4. Okay, so what I will do is like I will divide this into two parts from A1 to A4 and A5 to A6. Okay, now you can see I will have the subarrays that will always include this element A4 and lies in the left partition, which is subarray of this type A4, A3 to A4, A2, A3, A4 and A1 to A4, and for the right one we have A5 and A5 to A6. Okay, now for each subarray that is lying in the left partition, I will need to find number of subarrays, like for each subarray that lies in the left partition, number of subarrays where where this sum, let me write down clearly, number of subarrays where this sum goes to, like we need to find number of subarrays where this sum goes to. Okay, Now like if you focus over these part A4, A3 to A4, like for these sum, let it be S, okay, S1. Now this S1 not only lies over these positions like A4, A3 to A4, A2, A3, A4, A1, A2, A3, A4. It lies to some more extent. And what is that extent? Suppose if you are talking about A4. Now we have only this A4. Now we can also extend this A4 to A4 and A5. We can also extend this to A4, A5 as well as A6. Okay. And similarly we are able to do this for A3 to A4 subarray. Okay, and similarly we are able to do for each subarray that is lying in the left partition. Okay, so we will do that efficiently. Let S1 be the sum of all those subarrays that is lying in the left partition. Now this can be extended for the positions that is lying in the range for this one. Okay, so let S1 be the sum. Now this is the already this subarray that includes A4. We are going to extend this to A5. Okay, now this S1 will also get added. Note that we are talking about S1 only. Now this can also be extended to A6. So we are going to again add S1. So in other words, we can easily say let L1 be this position, let L be this position, and let I be this position, and let R be this position. So if S1 is the sum of the left partition, then I'll multiply it by R minus I plus 1. Okay, and similarly if A5 and A6, like A5 and A5 A6 is the subarray that is lying in the right partition, we can extend this one to A4 to like up to A4. Left end will always lie up to A4 and it goes up to A4 to A5 or A4 A5 A6. Similarly it can goes for A3 A4 A5 or A3 A4 A5 A6. Okay, so in other words, let's S2 be the sum of this right partition. So S2 into I minus L plus 1 is the required sum, where this left subarray will go to, like left partition as well as right partition will extend to the left row. Okay, so we need to find out the sum. So our sum will be like our sum where this minimum element will lie will be S1 into R minus I plus 1 plus S2 into I minus L plus 1. So this is the required sum, and let it be S. So our answer would be S into A4. Okay, so this is what we need to focus it. And one more thing I need to add is how you are going to compute A4, A3 to A4, A2 A3 A4, A1 A2 A3 A4 efficiently for every index. Okay, so I will tell you an easy way to do that. So let me move out to the next page. So suppose A1 A2 A3 A4 A5 A6. Yeah, suppose A1 A2 A3 A4 A5 A6 is the required array. Like this is the array. So first I will do the prefix sum of this one. So it would become A1, the next one would become A1 plus A2, next one would become A1 plus A2 plus A3, A1 plus A2 plus A3 plus A4, and we have A1 plus A2 plus A3 plus A4 plus A5, and we have A1 plus A2 plus A3 plus A4 plus A5 plus A6. Note that I am writing these things because this will help us to visualize the things very much clearly. So this is the prefix sum one time prefix sum. So let me take a prefix sum second time. Like for this prefix sum first time I will take the prefix sum of this one. So it would become A1 plus, okay, so this will be A1 only, and the next term would be 2A1 plus A2, and the next term would be 3A1 plus 2A2 plus A3, and the next term would be 4A1 plus, you can see it would be 3 times of A2 plus 2 times of A3 plus A4, and the next term would be 5a1 plus 4a2 plus 3a3 plus 2a4 plus a5, and the last term would be 6a1 plus 5a2 plus 4a3 plus 3a4 and 2a5 and finally a6. Okay, so this is the second time prefix sum. So suppose we need to find out the values lying in over here. Okay, so suppose we need to find out the a5 and a6, right? So a5 and a6, what is this? It is actually 2a5 plus a6. Okay, so are we able to find out with the help of this second one? Okay, so we need to compute the sum for this range a5 to a6. So looking at the prefix 2 sum, 2 times prefix sum. Okay, if I will subtract the prefix sum up to this position, like if you subtract the prefix sum up to this position, let this be p4 and let it be p6. If we able to do p6 minus p4, what we will get? Let me write down. If we are able to do that, then we will get as 2 times a1 plus 2 times a2 plus 2 times a3 plus 2 times a4 plus 2 times a5 plus a6. Okay, now you can see we are able to get this term, and there is something common over here. Okay, if we grab this common up over here, we will write down 2 times the prefix sum from a1 to a4. Let it be x. Note that x will denote prefix sum first time and p will denote the prefix sum second time. So x of from 1 to 4 plus the required sum that we want. Okay, so let it be s, the sum we want. Okay, so whenever we are like we have been asked to find out the sum from particular range from I plus 1 to r, to the right side we were going to use the prefix sum, and we are going to subtract the positions from, you can see the prefix sum, double prefix sum at r and double prefix sum at I. We will subtract the double prefix sum I at I from r. If you are able to do that, then we will also subtract this value. Okay, that is the length of the interval into the prefix sum. Note that the single prefix sum I am talking about over here, up to the range from 0 to the position I, if you are talking about. And similarly, if you have been asked to find out for the left hand side, we would deal with the suffix sum. Okay, so let's begin to analyze the code, how this will be done efficiently, and also I will explain with the help of examples later on for the sample test case that I have taken about. Okay, so let's move out to the coding part. Okay, so let me show the accepted code. Okay, yeah, so what I have done is like I have taken mod, I have defined mod as 10 raised to the power 9 plus 7. So n is strength size, and okay, and we have the prefix sum as well as suffix sum, and also we have double prefix sum and double suffix sum. We will need all that. Okay, we'll iterate from 1 to n. Note that here I am going to use a 1 based indexing. Okay, so prefix sum of I, we will store the sum of all strings up to the index I, and similarly double prefix sum is a prefix sum of the prefix sum. Okay, I hope you understand. And similarly we are going to do for suffix sum. And now this part, if you look out for this case s1, let me wait a minute. Okay, it doesn't matter. Okay, now you can see this part for this for loop. This for loop is going to find out the next smaller element for each index to the right of the current index. Okay, note that this right will store the position index of the next smaller element for the current index. Similarly, we are going to have the left. Okay, so this loop will assign all those, and it is nothing but the use of a monotonic stack. And here again I am going to do for the left part also. I don't know why I've written after this step. I don't know, I'm leaving the spaces for other work. So this is for the left, finding the positions of next smaller element to the left of the current index. Okay, also and this is for the query part, query left sum and query right sum. I will explain all those. So first let's move on to this main section. Okay, so what I am going to do is I am going to find out the current minimum, which is nothing but strength of I, and L is left of I plus 1. Left of I is the, you can see it is basically the position this one plus 1, which is actually the position A1. Here I am going to denote it by L, and similarly R right of I minus 1, that is over this position, which is the next smaller element to the right of this A4 minus 1. Okay, so I will compute the right sum. Okay, and also compute the left sum. Okay, note that left sum and right sum is nothing but this sum actually. If A4 is the minimum element, we need to know this sum, and if A4 is also the minimum element, we need to know the right sum also, which is S1 and S2. Now let's focus upon how we are going to calculate this S1 and S2. Okay, as I've already said, for calculating the left sum I need to work with the suffix sum, and similarly for the right one I need to work with the prefix sum. Okay, so suppose I am going to deal with the right. So I will first calculate the length of the interval, and this is the amount that we need to subtract. As I've already said, you can see I need to subtract the length multiplied by the prefix sum. Okay, so this is what I have done. Length D is the length of the interval multiplied by prefix sum. Note that we need to take care for the modulus every time when the answer overflows, and our answer is subtracting the value at this position P4 from P6. That is, this is actually the position I, and this is actually position R. Okay, note that we are converting everything in one based indexing. That's why I'm writing double prefix sum of R plus 1 minus double prefix sum at L. Note that this answer may be negative, so we need to take care of the modulus also. Okay, so this is not our answer. We need to subtract this one also, because our required answer is this sum plus S will be the answer, this one. So we need to subtract also. To subtract is the variable that is storing the value that we need to subtract. I will subtract that value and return the sum, that is the required sum for the right part. Similarly, you can do this for the left part considering suffix sum. Okay, now when we are able to find out this right sum and left sum, all we have to do is to multiply S1, which is the left sum, with the length of the right interval, which is I minus L plus 1. If I am working upon left sum, I will multiply with R minus I plus 1. So I plus 1 to R is the length of the interval for the length of the right interval, it is actually the right interval, and for the right sum we will multiply it with the I minus L plus 1. And why I am going to do that? Because as I've already said, we are going to extend this subarrays ending at A4 to either end at A4 or end at A5 or end at A6. Okay, basically we are calculating the lengths, how much we are going to extend it. Okay, and finally for the current answer, I will multiply current sum with the current minimum and add all those current answers for each index, considering each index as the minimum element, and finally return the answer. Okay, so this will give you all test cases passed, and if you guys have still any doubts, you can reach out to us through the comment section of the video, and thank you for watching this video.